Okay, so I think we've talked around the topic of machine learning quite a bit. Let's actually dive in, get into the nuts and bolts. We want to give everyone, a shortcut today, a look under the hood. The idea is to move past just the definitions so you can understand how to use these AI systems more effectively.
Exactly, because the fascinating part isn't just the definition, it's how these things learn. And for a machine, learning isn't. And well, it's not intuition. It's really about identifying statistical patterns in huge amounts of data. And the real power comes when it can then make accurate predictions on new data it's never seen before.
So that's the goal then, generalization. How does the machine decide where to even start? Is the approach driven by the kind of data we feed it?
It absolutely is. The data determines the whole game. The most common path is supervised learning. It's incredibly powerful, but it has a catch. It relies entirely on what's basically a cheat sheet, labeled data.
Labeled data, meaning the correct answer is already there.
Precisely. Think of training a system on thousands of house listings where you already know the final sale price. That's where you see algorithms like linear regression and decision trees really shine.
That makes total sense for prediction. But what happens when you don't have that cheat sheet?
Then you pivot. You move to unsupervised learning. This is for unlabeled data. It forces the model to find hidden structures all on its own. It's how a platform can group customers who behave in similar ways, even if you never define those groups. For that, we use things like k-means clustering or PCA.
And there's a third one, right? The one that's a bit different.
Reinforcement learning, yes, it's the outlier. Here, an agent learned by interacting with an environment. It gets rewards for good moves and penalties for bad ones. This is how AI learns to play chess or Go. It's also critical for robotics.
Okay, so we've got the different learning styles, but I think most people assume you just, dump a bunch of data into an algorithm and that's it. Is the prep work more complex than people realize?
Oh, it surprises everyone. Data preprocessing is where, 80% of the real labor is.
80%.
Easily. If you're not spending most of your time cleaning the data, you're essentially training on garbage. Let's just walk through the 5 steps. First, data collection. The quality of your data from sensors or databases that directly sets the ceiling for your model's accuracy.
Okay.
Second, the heavy lifting. Data preprocessing. We clean it, we scale it, we make it machine readable.
And is that the step where most projects fail? Because if the input is flawed, the rest seems almost pointless.
You've hit on the critical point, but let's assume the data is clean. Step 3 is model selection, choosing the right algorithm. 4 is training, where the model tweaks itself over and over to get better. And finally, step 5, testing and evaluation. We have to see if it can generalize to new data. We check things like accuracy, precision, recall, all those key metrics.
And this whole systematic process is why we're seeing ML transform industries, right?
Yeah.
In healthcare with disease prediction or finance with credit scoring.
The impact is undeniable. It's managing risk, flagging fraud instantly. But it comes with some serious challenges we have to talk about. The system is brittle. It depends on that high-quality data. So we're constantly fighting poor data quality, high computing costs, and the big one, explainability. We need to know why the AI made a certain decision.
But is it actually fair to blame the algorithm for that? Or is the lack of explainability just a reflection of the, flawed human data we fed it to begin with?
That's the core tension, isn't it? Machine learning isn't magic. It's a systematic process, and it's all driven by data.
So with that in mind, here's a final thought for our listeners. If we accept that data quality and all that pre-processing are the real bottlenecks, what fundamental assumptions about the neutrality of data itself might you need to question before an algorithm even begins to learn? Something to chew on.